他们家的可能被。哎。去 Lisa Tower。
Come in, please. Otherwise, no lunch. Okay, we start the second session of this morning. The first one is by Paul, and the title is Recent Black Hole Research.
Thank you. So I'll try and cover the latest results that we're working on in looking at black holes, and particularly the supermassive black holes, the very large ones. And a few topics that I'll go through. Of course, the gravitational wave detection that has been in the news, reported quite a lot in the last couple of years. And then, of course, the important part of this kind of research is to detect the actual cause of those gravitational waves. And then the latest things that we're working on, working at the event horizon, looking at motions at the event horizons, we have some detections, and then also imaging of the event horizon itself. And these kind of studies are one of the most powerful ways to look at the GR effects, general relativity effects, at the event horizon where gravity is strong. So common technique, as you will see, is interferometry to introduce the high angular resolution that's necessary. So gravitational wave detectors now, of course, certainly know about the ones LIGO, but also Virgo is now operating in Italy, and then Kagura is about to pick data in Japan. And the ability to have more than one of these detectors is very important, because one of the first things that we want to do is to be able to say that they are in time coincident, in the sense that you can detect them, for example, in these two LIGO stations in the United States and the Virgo stations, and also to check the signature of the gravitational waves. This is very important. This is where the theory is very important in predicting what the ringing should look like, and that they predict them at the various sites. And furthermore, the time delays between these detections is very important for positioning. So for example, for this particular event in 2015, the thought is that by the delay between these two stations, a separation of about 7 milliseconds in time allows you to position the possible target in the sky. In this particular case, the thought is that the source is in a large Magellantic cloud. And when you have other detectors, such as Virgo and Kagura, added in, the triangulation will then begin to narrow the possible detection zone to a smaller and smaller place. But in the meantime, how to actually detect them requires some traditional methods. This is the Subaru telescope in Japan that's built in Hawaii. And they have a very large camera that we have built called the hypersuprime camera. It has a field of view of 1.5 degrees, so that you can see, for example, EM31 in one picture, in one field of view. And Taiwan actually participated in construction of this project. Principally, an important contribution is the filter exchanger, which allows multiple filters to be slipped in to pick different colors of the images on the sky. And of course, this particular instrument, the primary purpose of this instrument is to do weak lensing of the dark matter. The dark matter will distort the shape of the galaxies, the images of the galaxies slightly, and from this distortion of the galaxy, we can deduce the matter distribution and dark matter distribution along the line of sight. For example, this particular large swath of sky, about 10 degrees, we can catch the distribution in the redshift space, and this redshift space is defined because we have multiple filters, which allows us to see the radiation at different wavelengths and allows us to deduce the dark matter distribution. So this is a principal experiment with the dark matter instrument, hydrosphere cam. However, it is also useful because of this large swath of sky at the same time. This was the event in 2017. This gravitational wave has a detection circle about like this. This is on the order of a few degrees. This is 10 degrees. And by scanning this, they are able to find this particular, looks like a neutron star merger event, where you can see that in the time frame from August 18 to 19 to 24th, a few days, this particular source had faded. Okay? Now, just from this, can you detect that this is actually the progenitor of the gravitational waves? Well, that depends on many other things. In particular, the light curve of this fading of the light with time after the gravitational event, and also the modeling of the spectral energy distribution, because we have the filters, so that we can see what the progression of this spectral energy distribution. So finding out that it's very important for theory to guide us, because it's the theory which make these predictions, which then allows us to conclude that these things are in fact the gravitational wave source. So this is one of the important direction that we're working on. So in Taiwan, we're working on the Subaru Ibis prime camera and the prime focus spectrograph that's being constructed. And we'll continue to look at the next generation larger instruments. And this, of course, we can also join the gravitational wave research directly. And I think in Tsinghua there are people working on that. The next topic I cover is about the orbiting of stars around the galactic center. In the galactic center, there's a supermassive black hole with a few million solar masses. And as it turns out, you can see stars moving very rapidly around the galactic center. So this is tracing a particular star called S2 in this orbit around the galactic center Sagittarius star, the supposing supermassive black hole. And you can see the size scale here. This is 1.05 arc second. So the orbit is only about on the order of a tenth of an arc second. The closest approach is about 1,000 Schwarzschild radius, 1200 Schwarzschild radius. And we now can track this over 26 years and determine this orbit very accurately. Okay? So this is a fantastic experiment which actually shows that when it approaches pericentric, it whizzes by in a number of days, so maybe a few days. And this very accurate tracking of this orbit allows us to track the velocity and the motion. Okay? So one of the first things that we detect, in fact, is that if we measure the motion of the S2 source relative to the supposedly Keplerian orbit, you will find that at pericenter, it deviates from this Kepler orbit motion by on the order of 200 kilometers, and this is actually the prediction from the gravitational redshift produces in the GRFX. So this experiment is made possible in the recent times, not only by the very large telescope in Chile, but also by combining the light in the 4 telescopes in the interferometer mode. So they take the light from each of these telescopes and then they combine them. The trick here is quite complicated. This camera, first of all, centers one of its light, one of its fibers on a guide star, which is about 6 arc seconds away. The purpose of this guide star is to remove the atmospheric effects which blurs the seam of this. So by centering on this, they can actually deform a compensating secondary in order to adjust the phase of the light coming into the telescope. And this sharpens the image quite a bit. In addition, it focuses on another fringe, on another fiber on this particular star very close to the center, about an arc second away, and that's tracking the fringe, which means that it actually tracks the phase between the different telescopes to maintain phase so that it's the interferometer, the optical interferometer, is phased appropriately. So it tracks the baselines and calculates the delay between the telescopes and actually corrects for it by checking on the fringe. So it's a very complicated thing before it's fed into the interferometer for the high angular resolution. So this particular interferometer has 6 baselines and has a resolution on the order of 3 milliarc second and a relative accuracy of about 40 micro arc second, which is very accurate. And because of that, It's very complicated just to show you not the details, but there's an awful lot of optics after it hits the primary mirror for purpose of, as I said, do the fringing and to do the wavefront sensing, and then to combine the light and also have this very complicated delay lines that steer the light between the telescopes to compensate the difference in the sky, the distance to the source. This very accurate measurement shows you, for example, day to day, it's marching along this orbit. Okay? But because of this interferometry being very, very accurate, what it can actually do is to reference the position of this S2 source and its primary galactic center. Okay? Well, why is that interesting? Well, it turns out the galactic center shows some flaring of its light. The flaring of the light turns out, shown here, on the order of minutes, as this flaring. This flaring, we think, is a hot spot at the last, as we call, the innermost stable circular orbit. Okay, that's at the event horizon, a spot of flaring. And we can track the motion of this relative to the S2 orbit. And the result is that that spot undergoes this kind of a circular motion. And we see this flare now a number of times. And this flare typically has a circular motion at the speed of about a third of the speed of light. And this turns out is consistent with what you might expect from the GR effects at the event horizon. So these very delicate measurements are state-of-the-art measurement at the event horizon. Okay. But still, this is not an actual picture. Okay. But for this kind of research, we can consider participating, of course, in these kind of experiments. But we are also looking at the very large telescopes that are being built now. And by participating in these, there are hopes that we can improve the light gathering and therefore the accuracy of these kind of experiments in the future. So now, I spend the rest of my time talking about the experiment that we are actually working on, which is actually to resolve the black hole image itself. So the target is to look at the closest examples, the largest example of supermassive black hole. The two best examples, turns out, is the one just shown before, the galactic center, and also a more distant galaxy, M87, in the Virgo cluster. These monsters, these very large black holes, turns out has a large swashing radii, and the shadow of this supermassive black hole is about 5 times the swashing radii, and has a resolution of 40 microarc seconds. Okay? So note that in the previous experiment, the astrometry accuracy is on that order. Now we want to exceed that in order to get there and see the image itself. So the technique is very long baseline difframetry at sub-millimeter wavelength. So we've known for some time now in the center of galaxies, typically there's an engine which is driving these jets, very fine focus jets in opposite direction at relativistic speeds. And as this goes out, eventually the jet heats the plasma as it works on the so-called working surfaces. And if you look at the radio images of galaxies, typically very messy stuff. If you look in the middle, you'll find that there's some interesting jet, which if you shift to a shorter wavelength, you see a finer jet, and finer jet, and finer jet, and finer jets, okay? So this is many, many times sharper than these images. In the optical, sometimes in the Hubble, you can also see this faint optical jet emanating from the center in the best cases. So in the galactic center, for example, this is a radio image, and on 8 arcsecond scale, we do see a very bright spot lying in the middle here. There's many other structures here, but in the very middle, there's this spot, a radio spot, that's very small and unresolved. Of course, we have ongoing studies looking at what happens around this galactic center. We're studying the gas motion, but this is a different story. I would like to just focus on the galactic center itself. So here, what we would like to do is to begin to look at the galactic center and image it with VLBI technique. So this particular spot, if you blew it up in something like 1,000 times or 10,000 times more, what we're hoping to see is a shadow of the black hole and the accretion process around it. What is that light around that? Of course, the black hole itself is black. What you see is the accretion luminosity of matter that's falling in. The shadow itself blocks the light from the background because it bends. The gravitation bends light into the black hole, so the light within 5 Schwarzschild radii are all bent into the black hole. But the stuff outside of it will be visible and can be seen in the emission. So the theory calculates, for example, that you will see a nice non-rotating black hole, no spin. You will see a shadow, and of course a maximum rotating black hole will have some squashing, and then you'll see some flattening of this image. And of course the outside flow, depending on the orientation, will have different patterns. So the objective here is to directly prove the existence of black hole, supermassive black hole, by seeing the shadow. The shadow itself measure the size scale. This is the metric. There are two things that we can measure: the mass and the spin. Okay, and then of course there are interesting processes that has to do with the infall process around the black hole and also formation jets. These have to come later. So, depending on the model, for example, this is a model of the M87 case. We expect the shadow to be about 40 microarcsecond. Its center has 6 billion solar masses, and its image, when we do VLBI, we expect to see a ring of bright stuff and darker stuff in the middle. And if you do more fancy theory, of course you can see jets and an accretion flow convolved with a VLBI beam, and the Greenland telescope at the summit will make a difference in the reconstruction of that image. Without the Greenland telescope, the image will not be so clear. So that's why we're building the Greenland telescope, which I'll tell you about. The Greenland telescope will then work together with ALMA in Chile, our telescopes in Hawaii, the SMA, and other telescopes in order to form a telescope uniform to the size of the Earth. And this is a plot of the atmospheric transmission. It shows that the transmission decreases as you get to higher and higher frequency, but at a very good site, we expect to continue to have transparency even up to 600 gigahertz. So this is the telescope being deployed to Greenland. We put it on a boat. Starting in 2011, we were competing for this particular telescope, which is the ALMA prototype telescope. We retrofitted over the next few years, assembled, pre-assembled in 2016, put it on a boat, gets to Greenland, and this is one of the deep water port with an Air Force base, US Air Force base on the coast, called Thule Air Force Base, and that's where we've set up. So this is Norfolk Naval Base. If you look very carefully, you can see an aircraft carrier here. And we basically assembled and then nearby and then put it on a boat here and sailed and reached here, and then we put it on a pad along the runway. So this is a zoom picture. This is actually where the telescope went. This used to be a landing pad or a storage pad for B-52 bomber. Thanks. And Google is great. You can actually see the telescope. A couple of seasons ago. This is a boat arriving. And then these are just pictures of being assembled. You know, we had to assemble the mount. It's not easy because in the Air Force Base there's not much, and we rely on some contractors from Greenland who are operating at the Air Force Base. So over the year from 2016, this is summer of 2016, this is the mount. This is the backup structure assembled in one of the warehouses at the Air Force Base. And then the next year, 2017, we lifted the backup structure and the telescope reflector surface onto the mount. It's fully assembled, and this is an effort where we used the industry in Taiwan to construct some of these containers and did the wiring. So it was a big collaboration with the Zhongkeyuan. And then finally assembling the receivers into the receiver packages. And these are the first phasing of the receiver package at JCMT in Hawaii before we shipped. And this, of course, the Aurora in Thule. We are sufficiently away from the North Pole to see the Aurora. You can see that in the distance from the Air Force Base. And this telescope fully assembled, and you can see that we are close to the North Pole. As you can see, the stars are surrounded. And then these are actually the first scan to detect the moon with the telescope. And then the first spectral line with the telescope. This is the CO line towards Orion. And then the first VLBI test at the beginning of this year in January 28th. And then after that, we had a successful experiment. So the timeline of this is that we're going to move to the summit from the coast in a couple of years. To do that, we have to establish a base, we have to find the housing tower, we have to transport, and we have to construct, and then we have to have window over operation. So this is coming. The reason we go to the summit is that the sky will be better there, and from there we should be able to operate at 3 times shorter wavelength, and give us 10 times the resolution. So now Taiwan is part of the Event Horizon Telescope, consisting of many institutions. We sit on the board as a founding member of the Event Horizon Telescope. In 2017, these telescopes participated. At the time, the Greenland telescope was not yet ready, so we participated via James Clerk Maxwell Telescope and submillimeter array, which are facilities that we operate from Taiwan. In 2018, you can see that now Greenland telescope actually is involved in this experiment now in 2018. So it forms all of these baselines. You cannot see very well, but it's truly a covering the entire Earth. So this is just some data to show you the importance of building ALMA. The ALMA has a very large collecting area because it has 65 telescopes. So before we phase up with ALMA, this is the detected signal on the sky. But after phasing up, meaning that you make all the telescope checking the phase and aligning the phase, you can see the signal is greatly amplified, and also the error pattern is greatly reduced. Okay? So this was one particular baseline from the submillimeter array to the Uran telescope in France, and for 400 seconds integration, and it works. So phase referencing we can now do at 1 second level for all of these telescopes. And this is the imaging of what we expect to see depending on the different kind of general relativity model, MHD model, as to what the image might be able to see. So the point here is that when you get the data back, you should be able to measure these images and look at these stuff in order to check what the theory will predict. Okay? So the theory is extremely important, just like the gravitational wave experiment is. What we actually see will be a constraint on those models. So you might expect and ask me now, what's happened to these experiments? So we've had several cycles. This ALMA first, 4th, 5th, and 6th cycle. The first cycle was in 2017. The results are about to be published soon. What do they look like? They are fantastic, but I cannot show you. We are forbidden to show you. But I tell you, it's really good. Particularly for M87. So I can say that the modeling is very good, and we are, in fact, seeing it. The galactic center is more complicated because it turns out the galactic center is closer. So it's physically smaller object. And that means that it's rotating faster. So within a day of the experiment, actually the image is rotating. So when we do this experiment, it's very complicated to restore the image. Just like you saw in the optical measurement, the orbiting motion around the horizon is on the order of minutes. So there are lots of structures that, in principle, in the future we can detect, but at the moment it's very difficult. But M87 is so much further, its rotation is physically much slower. So therefore this image is stable. So we can make a very nice image, and we have. So the nice thing about that is that over time you will see the structure across the M87 event horizon evolving with time. And that's what we'll be going after. And in 3 years' time, we expect to be up top. And then the image, which we'll show you in a few months, a really good image, will be even much better because we'll have 10 times the resolution. And of course, we are working on other objects now in this event horizon experiment this past season and coming up season. And Taiwan continues to be participating in this experiment. So as I said, we'll move to the summit, and this will improve the resolution by a factor of 10. So here's my summary. All of these experiments really depends on the angular resolution getting better. In the gravitational wave detection experiment, the problem is that it is still early. Okay? So we are only seeing some of the nearby events and the more frequent events. And these are relatively small black holes colliding. The bigger black holes colliding, of course, will not happen very often. Therefore, it will be very rare. So we will have to either have a very sensitive system or a long time baseline to detect enough examples. Once we detect them, of course, it's gone. So we have to actually get on top of the detection of the progenitors as quickly as we can. And so that depends on very large aperture instruments being built to follow up. But for the ones that we do know, we can study the structure, the event horizon, the structure at the horizon, the dynamics at the horizon, the radiation at the horizon, the physical processes at the horizon. These things are now within our reach. So next generation instruments that we're building will of course have much more resolution and sensitivity, and this will allow us to do much more in terms of studying the black hole physics. I'll stop there.
We still have time for questions.
Thanks, these are very cool results. Did you say, and I missed it, what are the projections? Are you going to be able to measure the mass and the spin of the black hole with some confidence error bars or something?
That's right. So usually to measure the mass of the black hole, you can either feel it, meaning the gravitational pull, see it. Seeing, of course, is not possible because it's black, right? However, the shadow is well worked out. It's 5 times the event horizon size. That's due to the light ray. We do the projection of the light ray. So as soon as we have that image, which we do, that size tells you the mass directly, because that measures 5 times the Schwarzschild radius. And then the shape will tell you where it's spinning, how much it's spinning. So the optical measurement of the flaring at the edge, the fact that it's actually rotating, immediately implies the black hole is rotating. And we can actually calculate how fast it's rotating. So definitely the galactic center Sagittarius star is what we call a curved black hole. It has rotation, right? So eventually these measurements will allow us to pin down how much spin there is. Directly from the image and directly from the motion around
So this flaring or this hotspot that you mentioned, so what exactly is that? Did you say it's correlated with the orbit of this S2 star? Or did I...
Yeah, so no, the flaring is not from the S2, it's from the galactic center itself. Where? Well, you can only be at the event horizon, right? Because everything inside is just pulled in. So the last innermost circular orbit, innermost stable circular orbit, is where we expect the remnant of material to be the last possible orbit. And the stuff that are falling in, radiating, we expect to be at that and further out. Okay? So that flare is coming from the accretion of material into the accretion disk, right? Because nothing has zero angular momentum. So it'll always hit the accretion disk rather than going directly in.
But I guess and it's not clear to me why there's a hot spot that flares periodically. If you have an accretion disk that's spiraling in, that sounds like a more steady state signal. Why do you get something that
why would it flare? Well, any number of possibility, right? Magnetic reconnection, acceleration, all sorts of physical mechanisms can.
Any other question?
When you track the motion of the star around the galactic center, does the dark matter there will affect the tracking or the motion or the velocity of that star?
Yeah, good question. As far as I know, nobody has looked at that particular problem. But surely dark matter is there as well.
Right.
Yeah. So, you know,
can you use the motion, velocity, and
yeah.
to tell how much
yes,
dark?
you can. So one of the things that the orbital motion, one of the things that people have been working on for the last 26 years is to track that orbital motion. Because one of the early conjecture was whether it's even a black hole in the middle, or a collection of stars, or some distributed matter. So depending on that matter distribution, that orbital motion will be different. So it's nearly very close to a clean Keplerian orbit, meaning a point source in the middle.
So no dark matter means?
Well, we don't see it.
Okay.
We don't see that effect, right?
Okay.
Will the dark matter be drawn in around supermassive black hole? So that it's also a singularity, right? It is gravity.
I have two questions. The first thing that the telescope you put in Greenland, it's pretty far to the north. Can you actually use that one to see the galactic center?
You cannot see the galactic center. It's too far south. So in the galactic center, there's a telescope called South Pole Telescope. And it's 10 meters in size. This one is 12 meters in size. And we place it in the North Pole specifically for M87, because M87 is the North Sky. So the experiment on the galactic center utilized the South Pole, but we also use the submillimeter telescope in Hawaii.
So the second question is that you have only a finite number of sampling in the UV plan for this measurement. How do you actually determine the size of the shadow? Because you make a model of them, or what? How do you actually?
You actually make an image, right? So, for example,
but you have only a few baselines. So actually, the image you make only comes from those Fourier modes. It's not a complete image, right?
Wow, that is the charm and great part about interferometry. Right? Is that with interferometry, you know it precisely when the light's coming in at precisely the UV distribution. So full sampling of the UV distribution, of course, will produce a perfect image. When the UV sampling is incomplete, you have an error pattern. But the error pattern is very precisely known because we calculate it, right? It is just perfect UV sampling minus the error function. The error function is that collection of sampling that's missing. Okay? You know that exactly. You can put a Fourier transform, you get the 30B. That is what they gave them a Nobel Prize for Ryle and Hewish. The fact that you can invert the problem. Okay? Inverting a problem for a complicated source is very difficult. For a point source, it's very easy, right? Because it's a point source sampling convolved with a sampling function, which is also a delta function, a collection of delta functions. So it turns out there are very powerful techniques that we use for aperture synthesis that can invert the image very accurately. We do it all the time.
But you are actually not really just detecting the point. You are actually trying to measure the size of the shadow.
Yeah, we make an image.
Okay.
We make an image, right? So all the images that's done from ALMA, PLA, SMA, VLBI, it's all been done with this interferometry that's sparsely sampled.
Well, the ALMA have many telescopes, so you can actually get quite good UV coverage at those places. But for this shadow, which is very, very small, you will need the longer baselines, which you have only a few of them.
Yes, you have to have sampled properly. Let me show you the image, but I cannot.
So suppose the gravitational wave detector, if a shot, can you point your telescope to that source and then take a picture, an image of the merger in the process of the video?
So everybody now is working on very fast slewing of the telescope. So as soon as the event is detected, people have to be notified. Usually that can be done on the scale of a minute. Okay? The gravitational wave, of course, is a little part, right? We're still detecting events now, much later, right, than the original detection. So key is to detect it right away, know that you've detected, and announce it quickly. And then, of course, if you have several sites, you have an error circle. So this is what's happening with that one. That's the binary neutron star. It was detected early enough that we could actually track the decay of the radiation and the spectrum. So that's a hot field called transient science, right? For gamma ray bursters, the same. You see a burst, immediately inform all the telescopes starts to get onto it. Yeah. But the actual merger event, of course, it's already happened by that time. So that's a very difficult experiment. But the submillimeter VLBI is very interesting because it's that resolution on the scale of 40 microarc seconds. So if we had events that are spiraling on that scale, what should we see? We should see a binary in the galactic nuclei. And we should be able to track it over time to see them coalescing. How? We need to have a good enough sample, right? There may be samples out there now that are binary, except we cannot resolve them, so we don't know. But we see lots of them that are actually rapidly varying. That's a hint.
Okay, let's thank the speaker again.